Hello everybody. Today I'm going to talk about autonomous coworking robot development with multimodal control based on model-based design. My name is Kazuki Ono, and I'm a robotics engineer at Kyocera Corporation. So in today's presentation, I'm going to cover first, background of our coworking robot system development initiatives, including the importance of robot hand development. Then I'm going to talk about our proposed SDK in order to develop robot hand efficiently. I'm going to then provide an overview of robot hand development using the SDK, model-based design, and MATLAB tool. I'm going to briefly introduce the robot system capable of multimodal control that we are aiming for. And then I will finish with an impression and conclusion. To begin, I'm going to start with the explanation of multimodal control system for coworking robot system that we are working from. We define the autonomous multimodal control system as a system that can respond to environmental changes reactively and autonomously, based on multimodal information obtained from vision and AI, as well as sensing information from sensors mounted on robot hands and arms. In today's presentation, I will focus on the development of a robot hand equipped with multiple sensors. Next, let me explain the background of coworking robot applications. Probably most of you have already that the shrinking global workforce and declining population could impact economic growth. Also, since consumers crave personalization addressing their unique characteristics, preferences, and backgrounds, the aging populations are a major challenge to serve diverse customers. That is why coworking robots with multimodal control system have attracted attention in recent years as a solution to these challenges. In this presentation, we will focus on one part of the multimodal system, which is the development of a robot hand equipped with multiple sensors. You know that the human hand is known for its ability to manipulate objects and perform tasks with great degree of precision, such as gripping and grasping. On the other hand, it is very difficult for a robot hand to manipulate objects as precisely as human hand, because robot hand is usually designed specifically to perform specific tasks. Since there is no practical general-purpose robot hand that can replace human hand to perform any task. Generally speaking, robot hand development is required for each specific task and object. This is a problem because this development requires a great amount of time and resources. That is why I think we need to think of a method to develop a robot hand that can respond quickly to various customer requests. That is where we introduce our proposal, which is a software development kit for robot hand control system development. We believe that by using our proposed SDK, we will be able to develop this robot hand system efficiently. On Chapter 2, I will explain the feature of this SDK in detail. Another approach that I'm going to cover in this presentation is model-based design. By using MPD shown on the right, front-loading the design process can be done, which then improves the design quality. Also, robustness can be estimated by considering variations and noise in virtual environment. We believe that MPD is another approach that can be done to develop robot hand quickly. Next, let me explain our SDK proposal for robot hand control system in detail. Let me talk about three features of SDK for robot hand development. First, the SDK is divided into discrete state-driven architecture, which performs sensor processing and control actuators. and OS part, which manages other applications. Second, the DST and OS part exchanges information via common memory. Third, DST part handles the design of control software related to the hardware configuration, such as the type of sensors or motor control. This feature is particularly important because the key to increase the development speed depends on how quickly the DST part can be built. From the next page, I will explain the feature of DST-A in more detail. One of the most significant features of DST-A is that it can be described by Simulink and has a common architecture in real and virtual environment. This means that you can design DST-A in a virtual environment and then replace it with the software from real environment. Next, I will explain the process used to develop the DST-A system. The first step is to design a DST-A hand system in a virtual environment using Simulink and MBD. Next, use the embedded coder of the MATLAB tool to convert it to C language. Then, directly implement the real DST-A system content onto microcomputer. Using this process, the system can be developed without programming. Now, let me explain more about the detailed structure of DST-A. DST-A consists of several tasks. The actuators and sensor mounted on the robot hand are defined as tasks. Each task is activated by periodic interrupt. Another feature of DST-A is that it has a discrete state-driven structure. This page's content is also explained in Chapter 3, so I'm going to briefly introduce it here. DST-A divides the program based on each possible state of the actuators and sensor. The important thing is by dividing the program into states, you can control program processing time. Therefore, real-time processing can be assured. Let me summarize the content of the SDK and DST-A. By using our proposed SDK, we believe that we will be able to develop this robot hand system efficiently. I explained that inside the SDK, the DST-A part basically handles the software design based on customer requirements. This DST-A has three features. The first is it has common architecture in both real and virtual environment. Thus, it is possible to seamlessly implement the content designed in the virtual environment onto microcomputer. Second is that each task of DST-A is activated by periodic interrupts. And finally, with DST-A, real-time processing can be assured. On the next chapter, I will provide an overview of robot hand development using the SDK and MBD and MATLAB tool. This is a practical example of our robot hand development. I will introduce a project type hand system that can control stroke width by acquiring velocity and contact force information in real time. This is a block configuration of robot hand real system. Next, let me explain the process of robot hand development using MATLAB that we carried out step by step. Inside this system block configuration, DST-A part is modeled by Simulink, and the parts of the mechanical mechanism, object, and contact force are modeled by SimScape branch body. The first step of robot hand development is plant modeling. This is a system block configurations modeled by Simulink and SimScape branch body. For example, DST is written using state flow to perform task scheduling and control system design. Also, contact force modeling can be represented using SimScape branch body contact force blocks. Next step is target setting of control cycle and processing time. The design items we need to set are control cycle, target processing time, and processing time interval. We set these items as shown on the left side. The operation chart for the task is shown on the right. As you can see on the operation chart, task 0 will first be activated. After that, task 1 will be activated followed by task 2 and task 3 at interval of 125 microseconds. So each task is set to activate periodically every 500 microseconds. After setting the control cycle and processing time, we then assign the state to both task 0 and task 1. As described in Chapter 2, we assign these states to DST based on state transitions. For example, for task 0, which is task for motor control, we have four states of velocity profile which are stop, acceleration, constant, and deceleration. We use Simulink function call subsystem to create and set table for target velocity and velocity feedback controller for each state. After assigning state to task 0, we also need to assign task status to task 1 similarly. Next step is to design the control system with DST. The control system can be designed to include sampling frequency and dead time. In this model, the sampling frequency is expressed by setting the state flow to start periodically, and the dead time is expressed by using the transport delay blocks. Body diagram can be easily drawn using the Simulink linearization tool. In the body diagram of a discrete system, you can see that the sampling frequency and dead time are included. On the next slide, we will verify this control system. Here, we can confirm that the motor velocity signal realized with a time constant of 3 milliseconds against the step signal indicated in yellow line. This corresponds to the zero frequency in the body diagram, and the validity of the control system was confirmed. Simscape multibody enables visualization of robot hand system dynamics. This scope monitors the result of motor velocity according to the movement of the robot fingers. Blocks from the dashboard library allow you to manipulate the model freely during the simulation. This video shows how inputting the target position during the simulation and pressing the moving button starts the finger velocity control. So far, I have demonstrated how to design velocity feedback control. Next, I will talk about force feedback control. The result of the simulation is shown on the video on the right. Here, the target force is set to 5 Newton. As soon as robot finger contacts the object, the contact force exceeds the target force value, and then about 60 milliseconds later, the stroke width is adjusted, and the contact force converges to the target force. By doing this, we can check for system performance and for early detection of system problems. On the next step, the DST part designer virtual environment is then converted to C language using an embedded coder. The converted code can be directly implemented into the real DST system part of the microcomputer. One advantage of using embedded coders is that it can greatly reduce programming time. For validation, the microcomputer is mounted on the robot hand. First, robot finger is controlled using velocity control, and you can see here on the velocity graph that it matches with the velocity profile set beforehand. As for force control, the contact force exceeds the target value at the moment of contact, but it converges to the target value immediately, similar to what happened during simulation. In Chapter 4, I will give an overview of algorithm development such as motion plans that we are working on in addition to robot hands, and introduce our initiatives towards multimodal robot systems. We also use MATLAB in order to model the robot arm. If the robot is ROS compatible, its model information will be an open source, and we will be able to import the robot model by using robotics system toolbox easily. We are also doing development on motion plan algorithms. In order to visualize the result of our algorithms, we combine them with the R model to simulate system dynamics. Moreover, we are working to use the model developed in MATLAB to operate in the actual machines. In this way, we have created a process in which the robot arm can be verified in both real and virtual environment. We combine all model components of vision, robot hand, and arm. Since our hand system was built using DSD, it is possible to assure the real-time performance and synchronize data communication with the robot arm component. Also, the arm can operate based on various data results obtained by other components, making it possible to perform multimodal control. Here, the calculation result from the dynamic simulation of the integrated model on MATLAB is inputted into Unity for visualization. In this way, by reproducing the user's environment such as lighting, shadow, object, and obstacle in a virtual environment, we can solve various problems and problems that may occur in real environment in advance. So design quality can be improved, and the development time and cost greatly reduced. So let me summarize today's content. I'm mainly in charge of the development of the robot hand system, and I created the model using MATLAB tool and built the system of DSD. I started using the MATLAB tool about 2 years ago, and in my opinion, the UI design was very easy to understand. Therefore, I think it is possible to build a system even with little programming knowledge. Also, there are a lot of applications that can help with the design of the control system, which reduce the development time and resources. I also like the fact that there are a lot of visualization tools such as Simscape Multibody. Visualization tools have made a great contribution for detecting system problems as well as for visualization data communication. The embedded coder was very useful. I think we have saved a lot of development time because we don't have to write script manually. However, there are few requests I would like to make. Simulation performance was degraded for complex simulation, such as contact force, multiple sensors, and robot complexity. Especially for contact models, simulation accuracy is very important and data reduction is rarely possible. So I hope MATLAB will provide tools to understand trade-off between performance and precision. Finally, for conclusion, there are the 3 things that I have introduced today. We are developing an autonomous coworking robot capable of multimodal control based on vision, robot hand, and arm in order to meet diverse customer requirements. We also introduced SDK and DSDA design to improve the efficiency in robot hand development. We believe that We can increase the development speed to robot hands by using the combined system of SDK, DSGL with MBD and MATLAB tools. Hopefully, this method could lower the difficulty for development in robotics industry. Also, if you have any question or comments about the content of this presentation, you can contact me directly at this address. That is all for me. Thank you.